Hello everyone, welcome back. In the previous video, we saw that while RNNs work well for sequence data, they do struggle with long sequences. They tend to forget some of the earlier information, memory problem, especially dealing with long sequences. And training can also become unstable for these long sequences. So the natural question is, how do we actually fix this? Well, see, that's where architectures like LSTM, long short-term memory, and GRU, gated recurrent unit, come in. Now, you might be wondering, in today's world of transformers and large language models, do they still matter? Well, I'm assuming, again, if you're a student of deep learning, you might have at least heard of transformers. And if not, again, transformers are the architecture behind the magic of ChatGPT and many powerful AI models we see today. See, but the fact is, even before transformers, right, we did have language models like Elmo and Flare, again in 2017, and they were mainly built using LSTMs, or a variation of LSTM, bidirectional LSTM. And even today, LSTMs and GRUs are still used in many real-world systems, especially in sequential problems like time series forecasting, edge AI, or maybe where resources are limited and you need lighter, faster models. So it's important that we understand, LSTM and GRU architecture. Now, understanding them again is not just about history, right? It's about understanding how this modern AI evolved and why these architectures still matter in practice. So in this video, I will walk you through LSTM and GRU step by step in a simple and intuitive way. But first, let's do a quick recap of a simple RNN layer and then jump into LSTM and GRU. Okay, let's do a quick recap of a simple RNN layer. We have already seen this. Okay, so again, let's say you have a simple RNN with 5 hidden neurons. To this, again, we give our input. I'm not unrolling in this yet in time. Okay, so xt. So we give xt as input. Again, we have at minus 1, which is the activation function from previous time step. Right? We use this and this to compute at. Okay, how do you compute at? Again, we initialize some weights, right? Wx, Wa. And we multiply these weights with activation function and the input x and also a bias term. And on top of that, we apply a nonlinear function, typically, tan h function. And we get the at. On top of this, we can add one more node and we get our yt. Okay. All right. And once you unroll this in time, this is how it looks like. We already went through this. Well, the reason I went through this again is just so that I can contrast this, a simple RNN, with a LSTM architecture. Okay. So please bear with me. So we have an LSTM, let's say. Okay, what are we going to do? So for LSTM also, let's start with a layer, a fully connected layer. Fully connected layer means it will also have some neurons, like something you are seeing here with the simple RNN. In simple RNN, you had 5. I mean, you can think of 5 or whatever. It also has, this pink color box in the LSTM is also a layer, fully connected layer with some hidden neurons. Okay, all right. So to this, we're going to give xt as our input. Okay. All right. So then again, we will have an activation, from previous time step. Okay. Same as a simple RNN. So I'm trying to keep things simple or same as a simple RNN, right? And then I'll show you where it becomes more complex or more different. All right. Okay. So now, then we're going to compute the output of this layer in the LSTM. Okay. So if you see this output, it looks very similar to what we saw the output from the simple RNN, right? Again, you take at minus 1, you multiply it with this weight matrix. You take xt, you multiply with this weight matrix. This time I'm calling this weight matrices as WGA, WGX, and then you have a bias term. Okay. And on top of that, you're going to apply a nonlinear activation function. Okay. Now, instead of calling this AT as in simple RNN, I'm calling this GT. Okay. All right. Okay. So now, again, you can see the GT there. So F1 is again the tan h function. So with LSTM, the most important thing is this green line, which I just draw, green arrow. So this is, think of this as a long-term cell state. Okay. So CT. So what is this long-term cell state? If it helps, think of this as a conveyor belt, which is running in parallel to the main sequence of time steps. Okay, so on this conveyor belt, information can jump onto this conveyor belt, stay there, and then get away, and as needed basis. Okay, hopefully that analogy helps. Okay, so again, this CT, it's like a long-term state, which kind of enables to keep some memories, store some memories, use some memories and throw away whatever memories are not needed. So that's what this CT is doing, this long-term state is doing. Okay. All right. So now what we're going to do is we're going to use a new gate called this update gate. Okay. We use this update gate to use only a portion of GT to compute a portion of GT that goes into this CT calculation. Okay. Again, if you see this, I have an equation for CT now. So ignore the first part of the CT. Okay. The later part, if you see, it shows UT. Again, this symbol is element-wise multiplication. So UT, this multiplied by this GT. Okay. So whatever the output of the pink cell, we are multiplying this UT with that. Meaning, this UT, its values, it's again a gate. It's a gate, but it's another fully connected layer, right? The output of this UT will typically be from 0 to 1. In essence, this determines what portion of this GT needs to be added to CT. Okay, so this long-term state, again, as I said, this can, retain some memories from previous time step, which can get some new memories, and it can throw away some memories. That's what this CT is doing. Okay, so this UT times GT is adding new memories. So whatever this current time step, whatever the information we are adding, right? So a portion of that goes to the CT. That's what UT multiplied by this GT means. Okay, all right. Now, how does this UT look like? So again, this UT in orange, this is also a fully connected layer with the same number of neurons as GT. Okay, but basically think of this as an update gate. And how do you compute that? Again, it's computed very similar to GT. You use AT-1, you use XT, and you multiply those with weight matrices and a bias term, and you apply a nonlinear function here, F2. So why is this F2? Because this is different from F1. This is logistic function. And this, because of this, the values of this UT varies from, 0 to 1. Okay? All right. So a portion of GT gets added to CT. Okay. Now what about FT? So FT, as you can see, FT is multiplied by this CT minus 1. Okay. So for this long-term state CT, there is also a previous state because it's at a time step T. So there is a previous state CT minus 1. So a portion of the CT minus 1 also gets added to the CT. And we do that with this, FT. So basically what we're saying is FT, think of it like a forget gate. So whatever this long-term state is, right, it's previous memories. A portion of that, we're going to ignore that. Okay. That's what this FT says. So whatever the portions we want the CT to forget. Okay. So this FT stands for that. And how do you compute this FT? Okay. So you compute this FT again similarly to UT. So you take the AT-1 and XT and you multiply with the weight matrices and bias term and apply the nonlinear activation function. This is also going to be F2, so logistic function. So both UT and FT, right, they vary from 0 to 1. And they in essence say that what memory should be retained with CT and what memory should be, what memories come into CT and what memories it should forget. All right. Okay. So now this CT, right, out of this CT, the long-term state, again, we apply another gate OT. So this OT determines what portion of this CT we ultimately want to output as our, final hidden state output, AT. Okay. So again, how do you compute OT? Same as before, AT-1, XT, use them, you multiply with weight matrices, apply the logistic function on top of it. See, all this explanation, right, of this update, forget, output gates, UT, FT, OT. See, while for the sake of explanation purposes, right, so that we can understand this long-term state, CT, is retaining some memories, right, it's forgetting some memories. To explain that, I have used this update gate, forget gate. But in reality, which gate function does what function? That is totally dependent on the weights that the network learns. Okay. All right. Hopefully, this gave you a brief understanding as to what LSTM network does. Now, once you get this final, AT, then on top of that, you can add another, final dense layer with one unit and you can compute your YT. So in principle, if you ignore what's happening inside this, you can treat this LSTM as a black box. And then, you can just use it same as a simple RNN. So in KRAS, if you want to use a simple RNN, you simply say KRAS.layers.simple RNN. And to use LSTM, you say KRAS.layers.LSTM. And then you specify the total number of units, these hidden units inside the layer. That's it. Okay, so in practice, it's quite straightforward to use the LSTM, but under the hood, it's a little bit more, a lot of stuff is happening. But again, remember, these weights are automatically calculated by the network as part of the training process. Now let's take a look at the GRU. Okay, so again, I'm using the LSTM schematic here to contrast it from the GRU network. Okay, all right. So when it comes to GRU, it's a little bit more simplified than the LSTM. So instead of having a AT and a CT, we just say AT equal to CT. All right. Again, we have AT minus 1, which is the previous the activation, or basically the long-term state at the previous time step. Okay. And how do you compute this AT? It's computed similar to the CT in LSTM, right? But instead of for CT, we have two gates, FT and UT, right? A forget gate and a kind of update gate. So here we just have FT, just the forget gate. So what we do is we take this FT, right? And then we have this 1 minus FT. So you multiply this FT with AT minus 1. In a way, it's kind of playing the same role as the forget gate in LSTM. And then you say 1 minus FT, it's kind of playing the role of update gate UT in the LSTM. Okay. And then you multiply this with the GT. So again, you have the same GT like LSTM, right? You have a layer here. Again, the layer in pink and the layer in orange, all these gates and GTs, they are all fully connected layers, meaning they all have, hidden units inside them. Okay. So you compute the GT, but, instead of saying UT times GT, having a separate gate, use the same gate, FT, and you just say 1 minus FT and you multiply that with GT. Okay. All right. As again, you can see that in this schematic as well. So how do you calculate this FT? So same thing, you multiply this AT minus 1 with the corresponding weight matrix, XT with the corresponding weight matrix, add the bias term, and then you apply a nonlinear activation function. Okay. So except now with GRU, you don't have update gate, you have a single forget gate. Right. Now again, you give the input XT, it's the same as LSTM. Okay. All right. So now there is one more thing here. So GT, how do you compute GT? So previously GT was directly computed from AT minus 1 and XT in the LSTM, right? But for GRU, to compute GT, you're still going to use the XT, the actual input, okay? And then you're going to multiply that with weight matrix WGX. But for the AT minus 1, you use another gate, RT, called the control gate, which determines what portion of this AT minus 1 needs to be used to compute the GT. Okay. So that's what this RT is doing. And how do you compute the RT gate again? Very similar to what we have been doing so far with other gates. You use AT minus 1 XT, multiply with weight matrices, apply a nonlinear activation function, F2, which will be the logistic function, and F1 is a tan H function to compute the GT. So hopefully you can see the similarities between LSTM and GRU and where GRU or LSTM differ from each other. Okay. So in GRU, instead of having two gates, FT and UT, you just have one gate, FT and 1 minus FT. And then the GT itself, right? Instead of directly using AT minus 1, you use a gate, control gate RT, you multiply that with AT minus 1, and then you use that to multiply with this weight matrix and add to the, weight matrix multiplied by the, WGX multiplied by the XT plus BG. And on top of that, you apply this, F1 activation function, which is the tan H function. Okay. Hopefully you can see the differences between LSTM and GRU. In practice, both of these work pretty well. Okay. One final thing I want to say with respect to both LSTM and GRU, again, these boxes you are seeing, the pink and the orange ones, right? They're all, in a way fully connected, meaning whatever the neurons, the hidden units we typically take, right? So those neurons, they're the same number of neurons inside each of this cell. So for example, if we say LSTM with 5 neurons, so you'll have 5 hidden units inside this FT, 5 units with the GT, 5 units with the UT, 5 units with OT. Similarly for the GRU, these are all, fully connected layers. Okay. All right. Okay, so that's it for this, introduction to the LSTM and GRU and, how they differ with the simple RNNs. But in principle, this LSTM and GRU, they work better in dealing with long sequences. All right. So that was the intuition behind LSTM and GRU. As discussed, these architectures were instrumental in overcoming some of the key limitations of simple RNNs, especially again, when we deal with long sequences. Okay, so far we have understood some of the major neural network architectures that helped pioneer sequence data modeling, whether it's simple RNNs to LSTMs and GRUs. But see, we still have one more very important architecture to cover. I know I have been hinting at it for a while in this playlist, and that's transformers, which is again the architecture, which was behind ChatGPT and is behind all the amazing AI models, LLMs, and agents we are witnessing right now. And it's my promise I will cover transformers in all its detail in later videos. But for now, please remember that sequence data can mean many things, right? It's time series, audio, text, or language. And even today, LSTMs and GRUs are still very relevant in dealing with many of these different types of sequence data, especially like time series, or even in many practical applications where we need lighter, faster models. Okay, so now before we move into the transformer architecture, there is one more important foundation we need to build. What is that? Well, if we want to work with text or language, how exactly do we represent this language so that we can build a deep learning model around it? Because at the end of the day, these models, right, whether it's machine learning or deep learning, they work with numbers, not raw words or sentences. So in the next video, we'll start by building this foundation and intuition first. And we'll understand how text is exactly represented in NLP or natural language processing, and how do deep learning models begin to work with language. So please stay tuned and happy learning.